for the introduction, having me here today. Good afternoon to all of you that are east of Massachusetts, and good morning to all of you west of Massachusetts. So yeah, today I'm going to be talking a little bit about some research that I did for my NSF Ocean Sciences postdoc fellowship, which I did at University of Wyoming with Mike Cheadle and Bobby John. I'll put all my collaborators up here on the last slide of the show. But as Ross mentioned, I'm currently at Woods Hole. So I kind of wanted to start off with the 30,000-foot view here. And so, what it comes down to is Earth's ocean chemistry, its climate, its habitability are really dictated by solid Earth processes over geologic time. These processes are in turn heavily affected by the behavior and distribution of water, whether that's water in the atmosphere, in the mantle, or in the oceans. And so water controls everything from facilitating mass transfer and chemical exchange to how rocks deform and behave both plastically and brittly. And so here is just a recent paper, kind of a schematic diagram with a recent paper from Ollie Agatu's group at MIT showing how cooling can actually be modulated by ophiolite weathering through organic carbon preservation. And so the main question here is, where is Earth's water and what controls its distribution? And if we think of plate tectonics as an internal combustion engine, we really have heat, which we consider to be the fuel, and we have water, which we consider to be the oil that kind of lubricates and facilitates the motion of plates. And so, water really is essential to all of these processes, but it's not well constrained as to where exactly it is. And that's something that I spent part of my PhD working on and kind of continued with this postdoc. And so if you want to kind of consider where is the water, here are three recent estimates of distribution of water between Earth's core, its lower mantle, transition zone, upper mantle, continental crust, oceanic crust, and hydrosphere. And the big takeaway from this is that, the estimates of where Earth's water resides can vary significantly. And so pinning this down is really critical. And so when it comes to water cycling in the Earth system, if we zoom into subduction zones, we can see that the transfer of water between surface reservoirs and the mantle really comes down to a mass balance between what goes in, that is altered oceanic crust, sediments, pore waters, and serpentinized lithosphere, and then what comes out, which is typically in the form of arc magmatism or dewatering in the frontal arc. And so, this is really critical stuff. And so today I'm going to be focusing on what are the inputs to these processes. How much water is actually in these systems, and how much water is being gained at mid-ocean ridges. And so returning to this kind of big picture slide, I'll really be considering the input side of the equation and focusing on mid-ocean ridge processes, and specifically mid-ocean ridge processes at ultra-slow spreading ridges. And so the real question that I've put on the bottom of the slide here is, how deep does seawater reach at mid-ocean ridges? And this is a pretty timely topic. There have been several papers in recent years. But when it comes down to it, faulting at mid-ocean ridges enables seawater to penetrate deep into the ocean crust. And for years, it was thought that this process was somewhat limited to the upper 3 to 6 kilometers or so of ocean crust. But more recent studies have really challenged this dogma, and they've shown from some recent studies along the Southwest Indian Ridge that you have deep hydration along transform faults that can extend down to 20 to 25 kilometers depth, and also recent studies that have shown that detachment fault mylonites also record deep hydration, but that they're somehow fundamentally different from transform fault mylonites. And so this type of work has major implications for not only volatile cycling, but also for understanding the rheology and how plates deform, for understanding the geophysical characteristics of plates, and for understanding hydrothermal fluid flow and chemical and mass transfer. And so this figure here is actually from that recent Bicart paper, which is kind of showing, how it's thought that water is getting down into these systems throughout these shear zones. And so the guiding questions that I really wanted to talk about today are, answering what is the depth that seawater penetrates oceanic detachment faults at ultra slow spreading ridges, and then are detachment fault and peridotite mylonites actually different? And so to look at and answer the first question, I'm going to be focusing on a field area along the Southwest Indian Ridge. But first, I wanted to kind of start with a little bit of an introduction and broad look at mid-ocean ridge tectonic processes. And so this is a figure showing spreading rate on the x-axis and depth below seafloor on the y-axis from a recent compilation of Grabermeyer in 2019. And the take-home message here is understanding that mid-ocean ridges diverge at different rates, and this in turn dictates magma delivery to the ridge axis. And as the spreading rate slows, magmatism will decrease, and faulting accommodates a larger proportion of spreading. In turn, these earthquakes may penetrate deeper into the lithosphere, as shown here, where full plate spreading rate, as full plate spreading rate decreases, the depth for earthquake activity also increases. And so as you get slower and slower plate spreading, earthquakes extend to deeper and deeper depths. In this figure, I also added a couple of more recent OBS studies from the 64-degree east region, as well as the 50-degree east region, both from the Southwest Indian Ridge. And so this map is actually a global map color contoured for spreading rates. So in the dark green, you have ultra slow spreading. In the orange and red, you have fast and ultra fast spreading rates. And so as part of my postdoc work, I really wanted to look at, investigating not only the depth of seawater intrusion along the Southwest Indian Ridge, but also incorporating a deep collection of samples available at Hui and available from Mike and Bobby at University of Wyoming. So the data set that I have includes data from Gackle, Mid-Atlantic Ridge, Cayman, and SWIR. The Mid-Atlantic data set includes Atlantis Massif, Cane, and 16 North. But today I'm really going to be focused on the Southwest Indian Ridge samples. And I actually had the privilege of sailing on this cruise in 2019 that collected these samples. And so when we look at slow spreading regions, what does the crust actually look like, or the lithosphere actually look like in these areas? And as I mentioned, faulting accommodates a large proportion of plate divergence, which generates these oceanic core complexes. And these translithospheric faults often expose lower crust and mantle rocks and are thought to root into these deep, high temperature shear zones, which generate highly deformed rocks called mylonites. And so as fault displacement increases, on these surfaces, the detachments may form oceanic core complexes, which are characterized by these domal corrugated surfaces on the seafloor. And so a little schematic of what this actually looks like. I kind of call this the traditional detachment model, where the detachment is actually cut at depth and terminated by a new fault, often an antithetic fault. And we see this quite often along the Mid-Atlantic Ridge. We see this along the Cayman Rise. And it was actually first described in the Atlantic. But at the end of the day, we have magmatism decreasing and these faults are accommodating spreading. And this cycle can go on and on as time goes on, which I'm showing going from the top panel down to the bottom panel, how this might actually look. And what's important to note here is actually where you would expect to find mylonites in this type of situation. And so as displacement along this fault increases, you're going to start exposing mylonites on the footwall of this fault within the axial rift valley. And so this is what we see when we go out in the field and actually look at these various areas, whether it be Cane, Atlantis Massif, Cayman, 16 North, et cetera. And so here's a region that we sailed to in 2019. This is the 45-degree east region of the Southwest Indian Ridge. And the full spreading rate here is about 14 millimeters per year. And this is a really, really fascinating segment. It's bracketed to the west and east by the Indomed and Discovery transform faults. And the regional geology here differs substantially as you go along the ridge axis. Now, if we start in the bottom left corner, down here in the west, we have a relatively magmatic segment where we're exposing peridotites, basalt, diabase, and some gabbros as well. The colors here, you can see diabase is in blue, gabbro is in yellow. And when we sample the actual immediate ridge axis, we do get quite a bit of basalt, and this is consistent with the magnetics that we see in this area as well. And the same goes for the region farthest to the east. This is another somewhat magmatic segment We collected primarily basalts in this region. But what was really interesting is throughout this entire middle region here, the area exposed essentially relatively fresh peridotites, both peridotite mylonites as well as undeformed peridotites throughout this entire central region here. And you can also see down here, we have several domes, several core complexes that are shown here in and around dredge 14 and dredge 23 up here. And what's really interesting about the locations of these dredges, if we look at dredge 23, for instance, the dredge was conducted on the outer slope of this rift mountain within the central oblique area. And so this is kind of antithetical to where you would expect to find peridotite mylonites in a typical detachment fault setting. As I explained earlier, you would expect to find these mylonites on the footwall to be farther in on the inward-facing slope of the ridge axis, and that's not what we see in this area. And so the samples I'm going to be showing you today are primarily from dredge 23 and dredge 14. But you can see we also recovered peridotite mylonites here and here at dredge 13, 12, and I believe 19. And so how do we get peridotite mylonites on the outer slope of this rift mountain? What is the model for that? And luckily, there's been some really fantastic work by our European colleagues on looking at flip-flop detachment models. And so the flip-flop model differs from the traditional detachment model, where the breakaways in the traditional detachment model, the breakaways are primarily constructed of basalt and diabase on the outward slopes. And eventually the detachment is cross-cut at depth, as I explained earlier. But in the flip-flop model, which has been documented farther east in the 65-degree east segment of the SWIR, detachment breakaways are composed of the previous detachment's footwall, which is what I'm showing here. And in this case, the original detachment fault, which is pink and shown in 1, is actually cross-cut by the next generation of faults at the surface. And so what this means is that if you look at where you're actually expecting to find the mylonites in these areas, they should be on the outer flanks of these rift mountains. And so this is something the flip-flop model is consistent with actually what we see in this 45-degree east area. And so again, this is just showing the different tectonic evolution of how this flip-flop model works. And as I said, this has been shown in the Southwest Indian Ridge. It's likely occurring at Gackle, and it's fundamentally different from the traditional detachment model. And so here, for the geophysicists in the audience, I wanted to show some of the magnetics data. What's really cool about this is you have these really strong magnetic signals sitting in these magmatic areas. But throughout this entire oblique segment where we're exposing significant amounts of peridotite on the seafloor, the magnetics are virtually nil, except for this one small area where you have a little bit of basalt that's coming up right in the middle of the ridge axis. And so since not everybody's familiar with the nuanced details of rock textures and peridotite textures, I thought I would start here with showing a hand sample photograph of an actual peridotite. This was from the Mid-Atlantic Ridge, and it's slightly oxidized on the surface. That's the orange that you see here. But in fact, this is one of the freshest abyssal peridotites that I have come across in Huey's entire collection. And on the right is the same sample in thin section where you can see the primary mantle minerals, olivine, orthopyroxene, and clinopyroxene, and spinel as well. But what's important to note here is that the typical mantle peridotites, this is a protogranular peridotite, are typically dry rocks. They have a few hundred parts per million water, but they have no hydrous phases in them. And on here, I've just given the mineral modal abundances of what you typically see in an average peridotite sample. And so the mylonites that we recovered are pretty astonishing. They're ultra fine grained. They range from protomylonites all the way up to ultramylonites. And this is just one of the hand samples from what we recovered. And so clearly these are highly deformed rocks that were deformed in a mantle shear zone during detachment faulting, which actually brought them up to the surface. And so when we zoom in on these samples and actually look at the textures that we're seeing, we can see these foliations of these amphibole-rich and olivine-rich layers. And you'll note that there is no orthopyroxene or clinopyroxene in this particular area, nor is there very much in the entire ground mass of the rest of the sample. And so these fabrics are clearly forming at high temperatures, but I also just mentioned to you that typical abyssal peridotites are dry and don't have any hydrous minerals in them. Amphibole is a hydrous mineral with about 2.8% water in it. And so the question is, where did this water come from? And on here, I've also given the mineral modal abundances. This is virtually a bimineralic olivine amphibolite. Virtually no pyroxene left in the rock. And so what we wanted to do is look at the compositions of these amphibole and kind of see if we can use that to tease out what the provenance of this water was. And so by looking at the compositions of these amphiboles, here I'm showing just the amphibole compositional boundaries on here with pargasite, magnesio hornblende, and tremolite. And so by looking at these compositions, we can see that we have quite a large range all the way from high temperature pargasite down to low temperature tremolite. And on here, I've plotted detachment fault samples, which is the rocks I just showed you from 45 East in the white circles. In the black circles, I'm showing data from Pridgeon et al., which was from transform fault mylonites from the Shaka and Prince Edward oceanic transform faults. And then also plotted in here are some data, the teal circles are some data from the Nicholas Ridge, which I'll talk about a little bit later. But what you can see here is this down temperature trend, which is consistent with exhumation of these samples along detachment faults. And so on the right, I'm also showing some textural observations from these samples. We can see here in the panel B, an orthopyroxene porphyroclast, and its rim has been corroded away to form pargasitic amphibole neoblasts, which you can see here. And if you actually zoom in on this pargasite and look at the textures of the individual pargasite neoblasts, you can see that they themselves are actually rimmed by tremolite, which again is consistent with this low temperature process during exposure along the detachment fault. And so the question is, where did this water come from that was this syntectonic water to form all of this pargasitic amphibole? And so we can rule out magmatic water based on amphibole compositions, because in fact, we know what magmatic amphibole composition should look like. Typically, they're enriched in titanium and potassium. They often have a lower magnesium number than the igneous mineral phases they're in, because they have been added by later melts. And so here I've just plotted titanium content versus potassium content for our 45 East mylonites in the white circles here. And they all have quite low potassium and titanium. And again, I have samples that have been metasomatized by melts and generated pargasitic amphibole, and those all typically plot out here. So we can rule out magmatic water for these mylonites. The next thing we can look at, which I spent quite a bit of my PhD focused on, is halogens. That is fluorine and chlorine, which we can use as another proxy to assess the source of water in our amphibole. Now, previous studies have shown that the mantle chlorine-fluorine ratio has a fairly narrow range, which I've plotted as this gray box on here. And in general, they're quite low. And so on the x-axis, I'm plotting silica and atoms per formula unit. And when we think about what the chlorine over fluorine ratio of seawater is, it's right around 35,000. That is because seawater has about 1 ppm fluorine in it and has about 35,000 ppm chlorine in it. And you can see that plotted on here are our samples at 45 East, and they are significantly higher than what we expect for mantle values. Now, I've also shown on here for comparison some magmatic amphibole from some oceanic gabbros that I also analyzed for this study, shown as the yellow squares and stars. You can see those define a relatively narrow range in this system. And I would point out that these gabbros that I've plotted on here include samples from Gackle, Mid-Atlantic Ridge, Mid-Cayman, and the Swir as well. But the bottom line here is these extreme enrichments in chlorine-fluorine ratios are likely not mantle derived, which is consistent with the looking at the compositions in terms of titanium and potassium abundances in the amphibole. So boron isotopes are another really neat tool we can use to evaluate seawater-derived influences from magmatic sources. And so boron comes in two different isotopes, boron 11 and boron 10. Their ratio expressed on the y-axis here shows that the boron isotopic composition of the mantle is about -7 per mil. And that's the solid black line you see on here. I've also plotted the 1 sigma uncertainties on that as the dashed lines. And this -7 per mil is much lighter than seawater's value, because seawater is quite heavy at about +40 per mil. And so for these boron isotope analyses, we do it through SIMS, which I've done at HUI. And these are in situ analyses. So I'm actually taking a thin section and analyzing an individual clinopyroxene porphyrclast, or an individual amphibole porphyrclast, to be able to identify these isotopic compositions. And what you'll see is that there's quite a range in these samples, from somewhere around mantle values or thereabouts, and it extends up to fairly heavy values of about plus 3 or 4 per mil. And these measurements can be exceedingly difficult to do, which is why you get some of these larger error bars on these samples. We're dealing with boron concentrations that are less than about 1 part per million in most cases. But again, we have another line of evidence that's suggesting that we have seawater mixing that's occurring in these samples to generate these heavy boron isotopic compositions. Now, another way we can get at this, since I arrived at HUI, I also started working in the plasma lab, analyzing the samples for strontium isotopic compositions, which is another proxy we can use. On here, I have plotted depleted Morb mantle as the black line, as well as depleted DMM and enriched DMM as the red and teal lines. And then up at the top, I'm also showing in the blue line what we take to be our seawater strontium isotopic composition. And so the way that we did this was we leached these crushed samples first to try to remove any low temperature alteration. And I've plotted here on the x-axis the extent of deformation in these samples. Now, the initial thought when I was doing this strontium work was that perhaps we're seeing a stronger seawater signal in the most deformed samples, which would be a crystal plastic deformation scale of 5 compared to a crystal plastic deformation scale of 0. Which is a protogranular peridotite. And you can see that didn't really hash out. There is some significant variability in there, but the fact of the matter is that these samples have all seen interactions with seawater. And so if you take the amphibole compositions, the halogen abundances and ratios, the boron isotopic compositions, and the strontium isotopic compositions, all of these taken together point to a seawater-derived influence as the source of the high-temperature pargasitic amphibole that we see in these peridotite mylonites. And so how are we going to constrain pressure and temperature? That's the next natural question that we want to try to answer. And to do that, we're able to look at the amphibole deformation history of these samples, which was done by a master's student looking at some EBSD data from some of these samples at Wyoming. And what they found was that the amphibole deformation fabrics were type 4, which requires at least 700 degrees C deformation for these amphiboles. When we do the pyroxene thermometry on these pyroxene porphyrclast rims, we yield temperatures of about 800 to 975 degrees centigrade. And so to pin the temperatures and try to get at depths, we can also use earthquake depths from OBS studies of tectonically similar areas along the Southwest Indian Ridge. And so here's one of the studies I've shown at the right. And if we take the maximum depth of earthquakes in these areas to be about 15 kilometers or so, and pin that to be our brittle ductile transition, which is anywhere from 600 to 700 degrees C, we can start to constrain these formation conditions for these peridotite mylonites to something along 18 kilometers or more beneath the ridge axis. And I also decided to put in some perplex modeling with this thermal structure. And so on here is just showing the phase equilibria modeling on here. As I said, the maximum depths of the brittle ductile transition we're pinning at 15 kilometers. And so whether we're assuming this is at 650 degrees C, which is the brown curve on the left, or 750 degrees C, which is the brown curve on the right, we can then, again, this is consistent with what we're seeing from the OBS data, where the textures in the phase equilibria that we're seeing, that is the mineral assemblages that we're actually seeing in the rocks, are consistent with the perplex estimates of this system. And so the implications here, this is just a figure I put together, kind of taking this all together, is really showing that seawater is able to penetrate these detachment faults to at least 18 kilometers depth at these ultra slow spread amagmatic ridges. But the lateral extent of that hydration is still really uncertain. We know water is getting down there, but the spatial extent beyond the immediate shear zone is something that we really don't have a great handle on at this point, and certainly requires more information. But I've talked a lot about the highest temperature side of these things with the Pargasite stability field. But if we return to the idea of the depth intervals between high temperature phases, the Pargasite formation at 18 kilometers or more, and we consider that the trajectory that this plate will be taking during uplift of the footwall, we also need to take into consideration the contributions from other hydrous phases, such as chlorite and serpentinites, which I've roughly shown on here with their thermal stabilities in this area over here. And so the question is, not only how deep, the extent that you get this deep high temperature seawater penetration, but also the extent to which you have hydration in this kind of what I would consider the intermediate conditions. And that's really not well constrained. And so in this figure on the right, just to give you an idea of the importance of this, I'm showing a Raman phase map that we did, that I did with Frieder Klein, and essentially showing you have the Pargasite in purple, and then you also have the chlorite in red, and the antigrite, which is a serpentinite mineral, in orange. And so more work really needs to be done on the stability of and the distribution of these other hydrous phases to really get at a more holistic approach and holistic understanding of the hydration state and the extent to which the plate is hydrated at the ridge axis. And one thing that would be pretty useful here would be some sort of multi-channel seismic to look at the serpentinization that's occurring in situ. And so everything I've showed you, we know that seawater is penetrating these mantle shear zones at the base of the lithosphere, but the question really remains as to how pervasive this is, and how do we get at that? And so if we return to the figure I showed you earlier of this general map of the region, if we look at this oblique segment in here from X to X prime, here's a cross section of this area. Now I explained to you that this is a really cool area because we think we're exposing a full cross section through this mantle shear zone at the summit of this rift mountain. And so the way that we really need to get at this to understand the distribution of and extent of hydration is really by going back to these areas and not just dredging. It's going to require using AUV to map these areas. It's going to require ROVs to be able to go down and sample these areas. And in the blue circles here, I'm just showing a hypothetical sampling program of what you could do to be able to understand what the hydration history is throughout this entire region. And so, for instance, we would expect that the crystal plastic deformation would be greatest within the shear zone and kind of taper out further out. And another proxy would be looking at the volume of Pargasite within these samples going from in the middle of the shear zone out. Is it a somewhat diffuse area of hydration, or is it a very sharp gradient that we get a very, very localized phenomenon of hydration? And this will kind of dictate whether, the extent to which this is actually important to consider when we're looking at global water cycling and water models. And this is something that we're hoping to do with the Germans in the next couple of years. Some of our collaborators have had a cruise funded. We're not sure what the date's going to be. We're hoping 2026 aboard the RV Sohn. But this is a really exciting area to be able to do this kind of stuff because in theory, we should have a full sweep through this mantle shear zone. And so kind of thinking big picture, the extent of lithosphere hydration could be more significant than we previously thought, but we really need to look at this in more detail by doing these kind of fine scale ROV sampling opportunities to get at not only the geochemical compositions and mineralogy of these samples, but also be able to look at what's going on structurally by getting some in situ oriented samples from these areas. And so, returning to kind of the big picture idea here, these global volatile flux models require answering some of these questions on here. What is ocean crust? What is the volatile content? What is the depth of hydration, the extent of alteration? And this type of work can at least start to address some of that when considering these bigger picture global processes. And so the take-home message here is really that at mid-ocean ridges, tectonics can deliver water down to the base of the lithosphere through these translithospheric detachment faults. And this is going to have implications for the rheology of plates at the ridge axis, for understanding the geodynamic processes going on, and for understanding the geophysical processes going on as well. And so I'll also point out that I've primarily been discussing tectonic water delivery through detachment faults today, but there's some really interesting places that I want to pivot to where we see both processes, both delivery of water through tectonics as well as delivery of water through melt addition to some of these peritites. And so this figure that I showed you earlier, I've just circled on here in red where we actually have evidence of some of this, some magmatic amphibole that's being delivered to these peritites and metasomatizing these peritites within these transform faults. And so this area in particular, this is at 39 degrees east. This is the Nicholas Ridge. This area was surveyed and sampled in 2020 by the SONA. And there were a handful of ROV dives within this intratransform ridge that brought back some really incredible samples. And so here's one of those samples. Looking at this thin section, for instance, we see that hydrothermal pargasite is situated in close proximity to this magmatic pargasite, which we see up here with these red arrows. And this really highlights the complexity of the hydration histories of these samples, because we have both magmatic delivery of water from below in the mantle, as well as delivery of water tectonically from the seafloor down these deep-rooted detachment faults. And so this is going to certainly require more work to really understand and tease out these deformation histories. But what's neat about this is the magmatic pargasite that we see in these samples is identical to St. Paul's rocks. And something we're working on right now is kind of comparing and contrasting the compositions, the trace element compositions of these pargasites from both St. Paul's and from the Nicholas Ridge. And so kind of applying what we've learned so far to some of those two fundamental questions that we started out with, it kind of comes back to the emplacement problem. Essentially, the work that we've seen in the last few years, looking at mylonites from transform faults, as I said, shows that they're being deformed at temperatures exceeding 800 degrees C and depths of anywhere from 20 to 25 kilometers below the seafloor. But the problem is, how are these samples brought to the surface in a strike slip regime? And if this is from uplift, then there should be a significant amount of overburden that was eroded away, which we don't see. Other models, for instance, that have been put forth in the 90s at the Garrett suggest you have these serpentinite diapirs. But this is something that there has not been a lot of work on, and certainly requires more study. And so when we look at the Nicholas Ridge, we have this lenticular this intratransform ridge, which is essentially exposing fresh peridotite mylonites on the seafloor. And the question is, where did this actually come from? And I've pointed out to you that the Nicholas Ridge mylonites are identical to the detachment fault mylonites with respect to deformation extent, textures, geochemical compositions, and mineral modal abundances. The only difference is these have some addition of melt in them from those magmatic amphibole that I showed you earlier. And so the simplest answer for this is that they are the same, in that they both were exhumed along detachment faults, brought up at the inside corner high, and then underwent transpression and uplift to form this intratransform ridge, at which time maybe they had some melt addition occurring. And so the model that we've kind of come up with is that the Nicholas Ridge peridotite mylonites were brought up by a paleo detachment fault at the inside corner high, with a plausible breakaway situated somewhere up here, And then tectonic reorganization led to transpression, which may have been augmented by the robust magmatic activity farther to the east, which generated the Mount Mahoney seamount. And this may have facilitated the imbrication of this paleodetachment footwall, i.e. cut it off. And then a subsequent transpression based on north-south trending thrust faults in the bathymetry are consistent with an uplift history, a later uplift history. And this kind of model is one in which we can avoid the need to have 20 kilometers of uplift along a strike slip fault. And so here's just kind of a view looking along this arrow of kind of what the model that we think is happening in this area. And then, here's kind of another model looking at it from the southeast. And so if this model is correct, we would expect to find a gradation from the deepest structural units where we had sampled previously here with a low temperature gradation going to the north, which would be consistent with a cross-section through about 20 kilometers of lithosphere. And so this is something that is eminently testable, and further assessments and dives are needed to substantiate this concept or this model. Unfortunately, this SONA cruise was cut short by the COVID-19 pandemic, and so they didn't actually get to conduct any more dives in this area. But taken at face value, this explanation for generating these peridotite mylonites in transform faults really gets around some of these issues that we have with how you get 20 kilometers of uplift in a strike slip regime. And so I'd also like to point out that these intratransform ridges are not entirely unique. If we look a little bit further to the east, this is at 46 degrees east. This is the study area I showed you, the northern extent of the study area I showed you earlier. We see the same types of features with these domal intratransform ridges, and they've also been documented at chain along the mid-Atlantic ridge. And so these are something that I think are a really interesting topic to investigate further, and there's a lot of potential in here to do so. And so when we think about where do we go from here, I think there's a lot of work to be done, and I've kind of listed a few avenues that I think are worth pursuing. And if any of you are interested in any of these projects, I'd really love to hear from you. But I'd really like to drive home the fact that we have the technology to be able to go out and do this in situ sampling and get oriented samples in the field. And I think this is a really critical way that we can pin down exactly what is occurring here structurally. And I hope that this approach gains traction in the coming years as not a replacement for dredging, because dredging is still a fundamental way that we can cover and survey large areas, but a complementary means to get at the more granular detail of what's going on in these actual systems. And so another topic that I wanted to briefly talk about is something that I've taken on since coming back to Hui, and I hope that some of you might be interested in this work that we're doing. But what we're trying to do is digitize the Hui rock collection. Hui has samples from the last 60 years, and they extend anywhere from the Gackle Ridge to the Southwest Indian Ridge, Mid-Atlantic Ridge, Pacific, from Cayman, and everywhere in between. And so what we're really trying to do is get all of the dredge data, all the rock dredge data that we have, all of the metadata that goes along with it, the rock descriptions, the thin section images, and the rock photo micrographs, and put all of them in one place that's easily accessible to both researchers and educators so that they can come in and know exactly what they're sampling. Any of you who have tried to find samples through some of the other databases that are available right now, that can be somewhat difficult because a lot of the time the nomenclature for those samples is somewhat generic. And if you're looking for something very specific, it's often hard to find in those databases, and you often have to just go to the repository and sort through all of these samples. And that's something I've had to do many times. And so the other major drawback right now is that the major databases do not have the ability to host images of large images of these samples, the kind of high-res images that we would want to be able to look in detail at these rocks. And so what we're doing is actually photographing these rocks, starting with the Gackle cruises from the Amore expeditions in 2001, and we're working our way toward the Southwest Indian Ridge collections as well. Hui has about 3,000 to 5,000 thin sections, and we are doing photo mosaics for all of those using our microscope. And we're hoping to get all of this information online and have it be available to the broader public. So the goal is you'll be able to search for specific criteria or sort by specific criteria by rock characteristics and have a rock photograph and a thin section of those rocks and be able to look at them in more detail. These are some beta images of what we're trying beta testing of some of some of the things that we're trying to put in here. We're still dealing with some bugs, but I would encourage you to reach out if you have any suggestions or would like to learn more about these. And I would also want to let all of you know that all of the rocks and samples that I talked about from from today's talk are also publicly available, and I would encourage you to come sample them. And if you have some interesting research questions you want to do, they're freely available to sample. And so here's just kind of a sampling of what we're doing with the thin section collection. Hopefully these will be useful to the broader community to be able to at least have an initial point from which they can start off some of their research projects or get more people involved in ocean science that are doing continental stuff right now and want to get involved but aren't quite sure how to do it. And so this is just a peridotite mylonite on the left, and then a gabbro. Both of these samples are from the Gackle Ridge. This is showing oxide amphibole gabbro contact, actually. And so I'll just put the acknowledgements up here. A lot of people have helped with this work. This is the research side of things on the left, and this is the curation side of things on the right. And all of the individuals who I appreciate their contributions to make this work possible. So with that, I am happy to take any questions.
Thank you, Ben. That was excellent. So if you'd like to ask a question, feel free to raise your hand or put it into the chat.
Ross, I can't see the chat right now, so if you can just read those.
Okay, sure, I can do that. So I have a question to get us started. So you're talking about having water in detachment fault systems that goes down to depths of up to 18 kilometers or so, something like that. So
in peridotite systems.
Peridotite systems. So wouldn't that imply that you have to have some kind of open, permeable network of either fractures or connected pores?
Yeah, so there's been some work on some of this tectonic pumping that kind of transcends the brittle ductile transition, where you can actually get fluid flow in purely ductile systems. So more work's going to be needed on that for sure, but it's there is the underpinnings of some support for that in the literature.
Okay. So we have a question from Steve Goldstein. Can you see that, Ben, or do you want me to read it out?
I'm just going to drop out of here and pull up.
So Steve's question is, he says, thanks, Ben. I know boron. In fact, Steve, if you're online, do you want to go ahead and read it out yourself rather than me doing it for you?
Steve? I'll just pull up the question and take a look at it.
I can read it out. It's I know boron concentrations in mid-ocean ridge basalt are sensitive indicators of seawater alteration. Did you look at that along with the boron isotopes, as it might explain some of the scatter? Also, could you use oxygen or hydrogen isotopes to trace water sources or temperature pressure conditions?
Yeah, Steve, that is a great question. So yes, we did contemporaneous boron isotopic measurements as well as boron concentration measurements, which I just didn't show on here today. And there is quite a bit of scatter in the concentrations. Right now, we're comfortable measuring the boron isotopic compositions down to about 0.4 ppm or so. But we did see, especially in the seawater derived samples, there were some significant boron enrichments to the tune of anywhere from 4 to 5 ppm or so. And yes, those did in a single sample. If I measured 5 different amphibole grains, you would see a positive correlation between the boron isotopic composition and the boron absolute concentrations. So yes, that was there. The oxygen isotopes, I'm interested in doing that. And the hydrogen isotopes are something that we're actually working on right now to be able to. So the issue you run into with running in situ hydrogen isotopes, and pardon me for those who do the bulk, but with the peridotites, really, I think it's probably really critical to do in situ on those. Hui just recently got a multi-collector. We have not tried to do DH measurements on the pyroxenes yet. A lot of the amphibole is too small to be able to do a steady DH measurement. We're talking the amphibole is typically less than 50 microns or so. But something that we're working on developing is being able to do DH ratios in these pyroxene porphyr class, 100 micron or so porphyr class. So stay tuned on that. And thank you for your question.
Okay, anyone else have a question for them? While people are thinking about it, I was just wondering, Ben, if you could tell us, like, of the number of rocks that you have in the collection at Hui, approximately what fraction of them are kind of currently curated in a way with metadata that can be accessed? Is this a work in progress, or is it something that you're close to being done with?
Okay, that is a great question. I would say at most about half of the rocks have IGSNs and are already situated in CSAR, for instance. I think we're kind of working one cruise at a time to get a whole package together. So we have dredge metadata, rock photographs, and thin section photomicrographs done. Right now we have almost all of the thin sections completely done. So if somebody, the website is not live yet, but it will be hopefully in the next month or so. And when that happens, please check it out. But if you're interested in a specific cruise, I would encourage you to just reach out to me and I can send you any data that we have from those samples. The big picture thing that we're trying to do is have all of this rock data available and have it transcend any one individual, because the problem right now is when you lose someone through a retirement or attrition or what have you, you lose all that institutional knowledge of the collection. And so we want to be able to have something that's a little bit more durable than that for anybody to be able to come and find this stuff. So if you want stuff right now, please reach out to me. And otherwise, I'll send this to you, Ross, if you want to send this out to the whole InterRidge email list, perhaps when we get it live for people to check out.
Yeah, that would be great. I think a lot of institutions are facing the same challenge, that as individual PIs retire or leave their institution, they leave behind a legacy of empty rooms full of rocks that have little way of accessing for others. So yeah, that's really fantastic.
Yeah, it's been.
Hi, Ben. It's Saurabh here. So
yeah, hi.
I had, thanks for the talk. It's very nice talk. So could you go back to your sampling strategy, please, in the Southwest Indian Ridge?
The map of the 45 East area?
The cross section of it, where you show how you plan to take samples from ROV or this one, 29.
Yeah.
So okay, I missed that. What is the displacement? I mean, what is the offset of this detachment fault now? I mean, the measured offset from the ridge axis.
From the ridge axis right now, it's about 20 kilometers from the present day ridge axis.
Okay. So yeah, that's good, because I also studied the rock samples from 64 degrees east on the new detachment fault.
Yes.
But because I think it has a less offset, so the rocks we had, they're collected by ROV, and they are all cataclastic. So we don't see yet any mylonite on the recent footwall of it. So for 20 kilometers, it's a great possibility to find them. Otherwise, with a small offset, it's difficult.
Yeah, so I'm so glad you brought that up, because that was a super interesting. I read your work on that, and that was a huge question, right? When we were writing this NSF proposal, why is it that 64 East does not see any sensu strictu mylonites, and yet we have an abundance of them here? And that was something that, you know, we had to be able to explain. And that was basically what the conclusion we came to, is there just wasn't enough offset yet to be able to exhume those.
Okay. Great. Thanks.
Yep. Anyone else?
Okay, well, if we don't have any further questions, I just want to thank Ben again for an excellent seminar, and look out for a link from us, hopefully for that geological data repository. We're going to be back again this time first Wednesday in October, and we'll be hearing about the impending eruption of axial seamount in a month's time. So this recording of today's webinar will be on the InterRidge website, and hopefully we'll see you all soon. Thank you very much.
Thank you.